cosine, cosine one. Okay. So I think we're supposed to have so I can just check that. Okay, so for number 6, they asked us to do sine and cosine, but we're only going from 0 to pi over 4, and then we're rotating about the x-axis and the y-axis. So obviously it's important that you know what your sine and cosine graphs look like. So when we think of our sine and cosine graphs, we normally think of it on the 0 to 2 pi axis. Our cosine graph is the one that starts at 1. And where does it cross the x-axis? Which of these? I heard a lot of mumblings, but no confident answers. Thank you, Garrett, for more mumblings there. When on your unit circle is cosine 0? Pi over 2. Woo! Okay, so we should have gotten our graph looks something like this for cosine, right? And then for sine, sine starts at 0, 0. And where on our unit circle is sine 0, other than 0? Pi. So we've got something that makes sense. Now, it's only asking for from 0 to pi over 4. So we're only looking at this little bit right here. Where they equal each other is that pi over 4, which makes sense because on our unit circle, that's the square root of 2 over 2 going on there. So we're only looking at the region bounded by sine x, cosine x on the interval. So we're talking about this region here. Okay, so that's how they got this little shape there. Okay, so we're rotating that around the x-axis. I'm going to go and erase all of this so as to not confuse us. Alright, so it is rotated around our x-axis here. You can see that there is indeed a gap. So we're going to have to subtract away that middle part. So we want to establish our big radius and our little radius. Alright, so our big radius, remember we always go from our axis of revolution. Always go from your axis of revolution to the edge of your solid. And that would be my big R, which would be our top minus bottom. And our top function was our cosine x. Our bottom function is our axis there, so 0. And that's why our radius, big radius, was just cosine x. So then our little radius, so again, subtracting out from our axis revolution to the edge of my gap, is my little radius, so top minus bottom. So that would be, this is my sine function, minus 0, which is just x for that. Okay, so again, our volume is integral to the area of the cross-section. And our cross-sections will rotate, we slice them up with their circles, so that's what we have pi r squared minus, take away our little one, pi r squared. Okay, do we have questions for our x-axis? So I don't listen to that. Okay, so then when we go to our y-axis one, that means we have to change everything to be in terms of y. Sorry. And so, again, we still have this as our little region here. I'm going to draw these a little bit bigger. Alright, so this was my sine x. This was my cosine x. But again, because we're going around the y-axis, then we have to do everything in terms of y. So this is our region. So I need to rewrite my equations to be in terms of y. So essentially I'm solving for x. So that would mean inverse sine of y equals x. And inverse cosine of y equals x. Okay, so those are going to be the functions that we're integrating. So now when I go to do my rotation, since we're going around our y-axis here, we end up not having a gap because it's right up against our y-axis. But when we look right minus left, we have that for this chunk of my solid, my right function is sine x, but then it changes functions for this chunk of my solid. So that's why we had to split up into two pieces here. We're essentially finding the volume of the bottom plus the volume of the top rotating around. Kind of looks like an ice cream on top. So when I go to do my radius, again, from our axis of revolution to the edge of my solid, my radius for this chunk here would be our sine curve. So inverse sine, I'm going to write radius here. inverse sine of y. Again, minus 0, so just inverse sine of y. And then when I go to do my radius here, again, for my axis to the edge of my solid, that's my cosine, so my radius for this guy, call it r2, let's call this one r1. Again, right minus left, so that would be inverse cosine of y. That is. So we again go back to volume equals I r squared, and everything needs to be in terms of y. So this here, this first one, pi r squared, represents my bottom part of my solid, and then my pi r squared represents the top part of my solid. Again, I had it split up into two chunks there because my function changed when we do right minus left, it changed functions at this point. So you had to figure out where they are equal, and they're equal at pi over 4, if you think where sine and cosine are equal. And so then the y value goes to that is 1 over root 2. So we have from 0 to that, 1 over root 2, or root 2 over 2 is what you guys are familiar with. And then from root 2 over 2 to 1. That's your boundary. Make sure you distribute, you multiply pi by both of these. I'll probably write pi next to each of them, just so I wouldn't lose it. Questions with that one with the y-axis? Okay, so again, when we did it with respect to x, and did our radiuses, axis revolution to the edge of our solid, it stayed the same function on top the whole time. So when we do top minus bottom, it didn't change. And when we did our inside radius, axis revolution to the edge, again, top minus bottom didn't change the whole time. So that's why we were able to knock it out with that one volume altogether. Whereas here, when we do right minus left, the function didn't change what was on the right, so we had to break it up. Basically, if your function changes doing right minus left, or if your function changes doing top minus bottom, you get a It's still the same general formula, though, of pi r squared being integrated. Okay, questions with 6? We'll go back and look at 2a, 3a, and 5. So let's just take a look at 5. Okay, so which part of 5 are we stuck on? Which part of 5 do we need to see? Anyone wants to pass up to 5?
Well, I put 5, but I don't remember which one I got stuck on.
Are you okay with the region, like what the region looks like?
Yeah.
With it like being the square root?
Yeah.
And
I
that?
don't remember when I started, so maybe it's not, but I remember.
Anyone, who else was my 5? Do you have a specific one you want to see? No one wants to know today. Okay, Amanda, let's take a look at an x1 and a y. Let's just do like the line that's off. So we've got line y equals 7. So I've got, here's my little region. All right, we had square root of, x squared. So here's my x squared, and then 2x. All right, so this is my little region. And we're rotating around y equals 7. So this is horizontal, so we're still doing dx here. This is for when we're doing dy. Okay, so when I go to establish a radius, always go from your axis of revolution to the edge of your solid, or my big R. So my axis of revolution, so top minus bottom would be 7 minus my bottom function, which was x squared. Okay, so that's my big radius. Now when I go to do my little radius, again, always from your axis of revolution to the inside of your gap. So again, top minus bottom for this would be 7 minus, and then my bottom function here was my 2x. Does that make sense? Okay. So then this is my radius that goes here, but you have to make sure you square that. Remember, it's pi r squared. And then this is my radius that goes here. You can make sure you square that. So we have our big R squared and R squared.
For D, if like x is supposed to be greater than 0, how are you gonna like switch it around the y?
So x is bigger than 0, which means y is bigger than whatever that corresponds with. Do you see that? So you would look at your y value that matches up with that. Does that make sense for the set of third? Okay, so then let's go take a look at a y. And we'll do the y-axis. I think that was our only y one. So we're rotating around here. So now we have to go in terms of dy, which is why we had to re-solve everything in terms of y. So when I go to do my little radius here, this is just way too small. Alright, so when I go to rotate around my y-axis, again, always from your axis of revolution to the edge of your solid, I need my big R. So my big R is right minus left, and my right function was the x squared, which is square root of y, minus left, which was just 0, so that's just square root of y. And then my little radius, so the axis revolution to the edge of my gap. So again, right minus left, and right is my 2x function, which is y2, minus 0, which just gives me y. So my big radius squared, when I go to do pi big R squared minus little r squared, my big radius squared is square root of y squared. My little radius squared is y2. Does that make more sense, right? And then let's go back up to...
Sarah,
Yes.
after you did those, I have a question about 6b. Wait, how did you find the interval, the y value?
The y value. So we want where the two functions are equal. We're assigning cosine equal on our unit circle at pi over 4, but we want the y value of it. So if you think of your graph, so we have cosine and we have sine. We know this occurs at pi over 4. Well, that's my x value. So what's the y value of that? What is sine of pi over 4? Root 2 over 2.
Okay, both.
What's 1 over root 2? That's just root 2 over 2.
Ah.
It threw me off first. So it's just the non-rationalized form of that. Okay, let's go back to 3a, and then we'll visit 2a before we go. Alright, so we've got our x cubed graph, and y equal to 8. Okay, so this is 8, this is y equals x cubed. We're looking at a. Alright, so we're rotating about the x-axis. When I go to rotate around my x-axis, again, when you establish your radius, always go from your axis revolution to the edge of your solid, that's your big R. And then for your little r, from your axis of revolution to the edge of your gap, we just do top minus bottom. So my big R is top, 8, minus bottom, which is just 0 there, because we're going to our axis of revolution, so 8. And that makes sense. When I rotate this around, it stays that solid length of 8 all the way out. And then my little radius, again top, which is our function of x cubed, minus bottom, which is again our axis, which is 0, so x cubed. So when I go to do my volume, again, I integral of big R squared minus little r squared. The big R was 8, so 8 squared. And little r was x cubed, so x cubed squared. Got questions with 3a? And then back. We've got x squared plus x. 0, y equals 0, x equals 2. Okay. So x squared plus x, we know that's going to be a parabola. It's not been shifted up at all because it doesn't have a constant at the end. So we've got a parabola. Or y, sorry, it's not that it hasn't been shifted. Our y-intercept is 0. So let's see. Let's go back to that. X times x plus 1. So we know it's going to be at 0, 0. At negative 1 will be our 2 x-intercepts. So there's a little parabola. And then we've got x equals 0, equals 0, and x equal to 2. So let's put x equal to 2. Alright, so we've got actually this region here. Alright, so we've got rotate, or am I looking at the wrong region there? X equal to 0, y equal to 0, x equal to 2. That's confusing. How can we be bounded by both x equal to 0 and x equal to 2?
I've been asking questions.
Are you guys seeing what I'm seeing here?
Yes, that's why I was confused and no one told me what they thought.
Tim, did you actually not know what to do? Right, so here's my issue with this one is, if this is x equal to 2, how can we be bounded by both x equal to 0 and x equal to 2? And then it said y equal to 0 in our graph. I feel like x equal to 0 shouldn't be a part of it, or x equal to 2 shouldn't be a part of it.
Oh, that happened on the other one. That happened with one of the other methods.
On this one, or
So the other method.
the disk one?
Yeah.
Okay, I'm going to take a look at this and see what the intention was for it. It looks like the intention was ignoring the x equal to 2 part. I mean, I guess technically, no, but then what's stopping that there?
I don't know, I did it all ignoring the x equal to 0 section.
Okay, yeah, so I feel like technically, if we go to x equal to 2, then that's going to be, right, that's stopping there. So x equal to 0, our graph, y equal to 0 has no bearing on it. I mean, y equals 0 just tells us that there. I feel like that is not a good way to
Yeah,
explain
the
that.
other way. But I saw a picture on there
That has the shaded in there. Okay, I feel like this needs to be better, better defined. AP does a much better job at I've never seen AP be sneaky with this. I feel like they would have said y equal to 6.
Maybe I did something wrong, but I did it with the other region and I got it right.
You did it with the other region together? Interesting. Okay, well, I'm going to take a look at that, see what the intention was. It looks like the intention was this region here, but I would have described it, I'll make a change to this for next year. I would have described it differently, where we would have said our parabola,
But like,
x equal to 0, and then
that doesn't have like a top down.
right, so that's why I'm thinking that when we have x equal to 2, that what they're using that for is to tell us that that's the ending of that, so that would give us our top out there.
The smart graph, isn't y equals 0? I mean, y equals 8 for top down. For number 3.
Oh, we're talking about number 2. Sorry, but you're correct for number 3. Sorry, I just drew it
Yeah,
down here. Yes, Justin.
Yeah, top minus bottom, which one would you choose for your bottom?
It depends on what you're rotating around. So if we were rotating around our x-axis here, top minus bottom, my bottom would be the axis revolution. If we were rotating around, let's say like this line right here, then when we do axis revolution of the edge, top minus bottom, bottom would be your function itself. Use that difference there. So guys, I think the intention here was that our y equals 0 just simply tells us that we have our intersection point there. And x equal to 2 tells us our intersection point there, which indirectly tells us our height of that. I feel like this is a terrible way to describe the region though. But it looks like the intention was to use this chunk here, based upon the little sketch that's there. But I feel like it should be described much better with saying our y, they're much more likely to say y equals that 6 value, rather than to say x equals 2. That makes it weird as to which we should talk about. So let's go take a look at A with this given region. So we're rotating around the line y equal to 9. So that's going to be above our region here. So when I go around that, y equal to 9. Always go from your axis of revolution to the edge. That's my big R. So my big R would be axis of revolution is 9 minus my edge, which is my graph of x squared plus x. Make sure you put that in parentheses. And then when I would do my inside region, little r. So then little r would be axis of revolution, so 9 minus this piece here, which would be 9 minus 6, which would be 3. Yeah, I can't just tell like what they have here. Just a nice. I'm gonna throw this one out. Alright, yes, Tim.
Wait, is that y equal to 6? Or what is that?
Y equal to 9. Y equal to 9 is
No,
another
no,
one.
the black, the,
Oh, this here? That was 6, yeah.
why?
Because, so they're saying that x equal to 2, when I take 2 and put it in, 2 squared plus 2 gives me 4 plus 2, which is 6. So my y value would have been 6. That
Oh,
was
the
actually
just
6
thing.
meters. Yeah, which I think that's what they're trying to communicate there is, if we're bounded by x equal to 2, then that's where we are cutting off, and that indirectly tells you your height there. I don't feel like that's a very good explanation. Yes.
With the other region.
Yeah. You got that same value there.
Okay. Doing the other region gave me those two.
Really?
Yeah.
Interesting. Okay. Wait. So what it should have said then, if they wanted this region here, if they wanted that region, this is what the description should be. Is our function. I like the y equals 0, x equals 2. That just. Okay. I'm sorry, I can't resist it. Let's do the region for this time. Alright, so if we're rotating around y equal to 9, radius to the edge, so there's our radius. Our big R then would be top minus bottom, so 9 minus 0, which is just 9. And then my little radius to the edge, which is based upon my function, so my little radius then would be 9 minus my function, and again, make sure you distribute that with my function, x squared, makes sense. Distribute that. So, yeah, that's good. Okay. Note. Okay, I'm sorry, guys. That was not meant to be sneaky. Alright, do we have questions about that one? Now that we've decided what region that is supposed to be. Okay. So today what we're doing is our volumes by cross sections. And this is our last kind of volume. So we had volumes by disk, volumes by washer. And those were basically the same thing in that when we rotated around, that means our cross sections are circles. Disk meant that we didn't have a gap. So like if I were to take this region right here and rotate it around my my x-axis, there would be no gap. Washers, when we do have that gap, we have to basically subtract it out. So I'll come back to the fact that our volume equals the integral of our area of our cross-section. And our area of the cross-section when we rotate is a circle, which is why we were integrating pi r squared. We brought the pi out in front, and if we had to subtract away something, we did volume of the outside, so pi r squared with big R, minus pi on the little side, or the inside, which was little r, pi r squared. So today what we're looking at is we're not taking a region and rotating it. Now we're taking a region and we're using that when we do cross sections, there's a variety of shapes that we can have. So we are no longer just integrating pi r squared, but we're going to be integrating the different areas as to what we did for our warm-up. So let's take a look at our warm-up here. These are some common cross-section areas that we use. Squares, semicircles. What kind of triangle is this? A right triangle. What else do we know about it? What does this mean if the two legs are congruent? Starts with an I. Isosceles, good. So we have an isosceles right triangle. I think I heard someone say it's a 45, 90 triangle. Good word, Tim. And then what type of triangle do I have here for number 4? Equilateral. And 5, this is another isosceles right triangle. It's just notice that instead of my side being one of the legs, my side is the hypotenuse. Okay, so that will change your area formula. Okay, so for number 1, what did we get for our area? Side squared. Yeah, that was nice and easy. Now for our semicircle here, we know it's pi r squared is our area for an entire circle. For a semicircle, we'd want only half that. But my radius is not s. What is my radius? Good, so s over 2. So when you plug that all in, what'd you get for your area for this one? Simplified all the way down, we should have gotten, did we get pi over 8 side squared? Okay, let's take a look at that. So we have pi r squared divided by 2, so I'm going to do pi over 2. And my radius would be s over 2 quantity squared. which would be pi sine squared over 2 times 4. So pi over 8 sine squared. Okay? So that'll give me my area of my semicircle. If I needed a quarter circle, what would I do with that? Divide by 2. Good. Okay. Number 3 actually isn't too difficult. What's the formula for area of a triangle? Good. 1/2 base times height. What is my base here? What's my height? Woo! So we have 1/2 sine squared. Also, too, isn't this just half of the square? So my area of square sine squared. When my leg, with one of my legs is the side, then it's just half of that. Okay, equilateral triangle required quite a bit more work. Alright, for an equilateral triangle, again we have our areas 1/2 base times height. We have 60 degrees all the way around, so when we draw that height, that altitude, so a 30, 60, 90 triangle. And our relationship, ooh, I love it when the special right triangles come back. So my relationship between my hypotenuse and the short leg is my hypotenuse is double my short leg. So my short leg should be s over 2. It's going to be this here. Which means that my long leg is what? Root 3 times that. Good. So s root 3. Okay, so that's my long leg. So when I go to do my area of this, 1/2, my base is the whole thing, so not just s over 2, but rather s. And my height is the s root 3 over 2. And what did that simplify down to? Good, root 3 over 4 sine squared. Okay. And then for our triangle down here, again, a little bit more work. And we have it to 45, 45, 90. But now instead of giving us the leg, we have our hypotenuse. And our hypotenuse in a 45, 45, 90 is our leg times root 2. So if my hypotenuse is s, when I go to solve for my leg, divide by root 2, divide by root 2. We have to rationalize that, so multiply by root 2 over root 2, and I get s root 2 over 2. So when I go to do my area here, actually, did we need that? Yeah, we need that for our leg. Okay. So 1/2 base times height. Again, we could just use our sides here. You didn't have to go through and do your height again. So height is just perpendicular. So my base is s root 2 over 2. My height is also the same thing because it's isosceles, s root 2 over 2. So we have s squared, so we get a 2 on top. We get 8 in the bottom. So did you guys get 1/4 sine squared? Did you actually get that? All right, so our area for this one was 1/4 sine squared. So all we did here was just some geometry, but leaving it in terms of our side. So this is going to be super beneficial for us today. We take a look at these. I have area that's squared is based upon my side, which is sine squared. Area of our semicircle. Okay. Area of my semicircle is pi over 8 sine squared. Area of my isosceles right triangle with my side being a leg is 1/2 sine squared, or just half the square. I feel like it's easier to think of it that way. The area of the equilateral triangle is root 3 over 4 sine squared. And then this is again an isosceles right triangle where my hypotenuse is the side. My area is 1/4 sine squared. So our basic beginning thing for volumes is that volume equals the integral of the area of your cross section. So far, we've only done cross sections that were circles because we were rotating around an axis. And so when we sliced that up, then we got little discs or little washers. Well, now, instead of rotating our region, we're going to have squares perpendicular to our region, or semicircles perpendicular to our region, or triangles perpendicular to our region. So instead of integrating pi r squared, we're going to be integrating the area of a square. We're integrating the area of a semicircle. We're integrating the area of a triangle. Now you could, every single time you encounter one of these, derive the area formula. Or if you happen to remember these little shortcuts here, when you see that it says, all right, area or volume created with semicircles perpendicular to the x-axis, you can immediately know I'm integrating pi over 8 sine squared. So memorizing these little shortcuts will make your life a lot easier when we go to do our integration work. I want to go ahead and kind of give you an idea of what it is, the shapes that we have when we do these cross sections. So let me first pass this out to you and then I'll illustrate them. Yes.
Can I go to the bathroom?
Yeah. I think it,
And 5. And make it
maybe don't
Yes.
When are we gonna do unfolding mathematics?
That was geometry.
Yeah, we just
I still have Ian and I mean, maybe same exactly.
And that's the last time that you
No.
Give me air conditioning.
I still have it. They made that? Yeah, this one was Eric and Ian's.
Oh.
Well, it's not super nicely greased, so that makes it easier to leave it together with some tape. I assembled it. Does that make it easier? Yeah. They folded it. They did the folding. I assembled it.
Can you do that with a sphere?
This is probably the sphere's completely smooth, so
Yeah.
it wouldn't be like a perfect sphere.
We can do it big enough.
But you can like keep
More
adding in
control.
more and more and more and more.
How long does that take?
I think this took the entire class time actually.
Oh, we should definitely do it.
Yeah, can we actually?
Some of these other ones are a little bit easier.
We had this before, I can't do anything like that.
It was the day of the SOL. I had you guys in class, and I was like, I like math, but I don't want to be too mean to make you do math after you did math according to me. Okay, thank you, Shrek, for passing that out.
We're looking there.
Something I'm going to show you. It's wooden blocks. Okay, so again, the idea what we have happening here is that we're given a region. Okay, so I'm going to kind of jump ahead for a little bit. Let's take a look at number 2. So it says, find the volume of the solid whose base is the region inside the circle if cross-sections taken perpendicular to the x-axis are squares. Oh, how convenient. I have a circle base here. I didn't even think that. That's awesome. Okay, so let's go ahead and draw our region. Our region is x squared plus y squared equals 9. What does that mean? What does that look like? A circle, okay. What is our radius of the circle? I think I heard a feeble 3. So our radius is 3. So let's go ahead and draw a circle radius 3. Do your best with it. We're not looking for perfection here. Okay, and it says cross-sections taken perpendicular to the y-axis are square. So what we have happening is that this is our base, and then coming out from our paper are squares, where our squares lie on it. Okay, so we have a bunch of little squares coming out. Okay, so that's going to create our shape. So what we have here is our base is a circle. So our base is a circle, right? And what we have coming out from there are squares. So a bunch of little squares are coming out and forming our solid here. So we have a bunch of little squares coming together, and it creates that solid. I'm going to go ahead and pass this around so you can kind of see what's happening with it. So this is just, we have a variety of cross sections that we can do. If we were to take it and rotate around, then we would have circles to be our cross section. But here, We're not rotating it. This is our base. We have a flat base. Our flat base is the region. And then we have squares coming out from it where squares are aligned. Yeah. So these would be another couple of examples. So as you can see, when we have squares as our cross sections, that's going to create a different region than when we have triangles as our cross sections. So here, again, it's a circle. And this one we have isosceles right triangles where the leg is lying on the base. And you can see that changes what the shape of it looks like. So that's what's going to change your solid. So depending upon your cross section, that changes the solid and that changes your volume. Yes,
So
Gary?
those squares are coming at.
They're coming at you. Yeah. So you have little squares coming at you. This means in little triangles.
Not side coming in, or like side,
Like imagine.
like that, or is it like,
Yeah, like that. It's like
yeah.
what's
So-
that on the side of the top?
This is not our same region, but similar idea. Here we have rectangles coming out at us.
Okay.
So these are just a few of the cross sections, but we have our infinite little cross sections. Slices.
Yeah, wait, why? What's the matter? What?
It's creating a solid. So
Oh, so it's creating our shape.
yeah, we're creating a 3D shape with that. So what we're doing is we're finding the volume of the solid that this
So
creates.
this is a cylinder.
No.
If they were all the same height, kind of, but what we have is that our squares are based upon the radius of our circle. So as we go along, you can see my squares will be different widths. So this, as it comes, so because the square is it's the same on the base as it is for the height. So here it's going to be a little square. Here it's a much bigger square. So they kind of increase as you go along and they come back down.
Yeah, so if you had them superposed together, it would be a cylinder. If they were all touching, how would it not?
The shape's going to come around to you in a moment, and you'll see it. That one looks kind of like the top of. No, not lipstick. What was that one? I don't remember. Yes, Chelsea.
So it feels like it was kind of looking like a cylinder, but it's actually not a cylinder.
Yeah, like if you were to look at it head on, it would be kind of like a cylinder that has that circle and you know it's a solid. But the sides slope down, if you would, because the squares are smaller on the edges. Yes.
Wait, so if you're looking at those, like, how can you tell it's a base circle? Because you can't.
This one, the base circle, this one, it's not.
Okay, but for this one, do the like different specific like cross-section triangles like curve to fit like this circular shape?
So the circles, as we go to the edge, are going to be smaller and then larger, not circles, these are triangles. The triangles, as they go along, it's going to be the width of the shape of the wood. So over here, it's a little tiny one, and then as you can see right here, it's going to be the largest one. This green one's the largest one.
Okay.
Now, instead of having them do like a million of them,
Yeah.
we just did 7 cross sections. So you can see it's smaller on the edges and biggest in the middle.
Okay.
Yes, Gary?
So the larger the width, taller the height.
Yeah, that's a very good way of putting it. Right, because what we have is our square, the base is based upon our region, and so when our region is wider apart, then our height of our square is going to be wider, whereas over here, our region isn't as wide, so the square won't be as high. So kind of, it's like a cylinder that got the edges shaved off a little bit, kind of slopes down. Okay, so we have different regions to start off with, and then we have different cross sections. Now, within the problem, they will always tell you your region, and they will always tell you your cross section. So, for example, number 2 here, it says our cross sections are perpendicular to the y-axis. We're going to actually rotate that, but they're squares. Whereas for number 1, our cross sections were equilateral triangles. Now, all that that does for us in terms of our integrating is it just changes which area formula we're using, because our formula is the same as it was before. It's just the integral of your area of the cross section. It's just now our cross sections are not always circles, so it's not always pi r squared. It depends on what your cross section is, but they have to tell you what your cross section will be. Okay. So what we did for our warm-up are our shortcut formulas. So let's go ahead and copy that down. So I'm just going to draw a little square. Our area was side squared. And again, this is where my side is what's lying on my region. We had a semicircle. You know what? I'm going to draw it. I'm going to draw it this way. Because a lot of times we're going perpendicular to the x-axis. So my side is, again, the height, not the hypotenuse. Diameter of our circle. So our area shortcut formula was pi over 8 side squared. We had, I think next was our isosceles right triangle. And this is the one where our leg is sitting on the region. Okay, so this is just half of our square. So this is 1/2 side squared. And I'm going to go ahead and draw underneath it just so you know that it's different. When we have an isosceles triangle, where our hypotenuse is the side. That was our weird one. Or not too weird, it was 1/4 side squared. And our last one that I made you go through and figure out was our equilateral triangle. So our area for this was √3/4 side squared. Okay, so those are shortcut formulas that we did for the warm-up. And if you remember those, then you don't have to derive your formulas every single time. But if you forget them, obviously you can derive the formula. And again, the fact that this one is half the square should hopefully help you remember that's just 1/2 side squared. Okay, I do want to go ahead and show you, I believe I've got another illustration of our volumes on these, of our cross sections, and I think this is helpful in visualizing what's happening as well. So I do want to take the time to look at that. Except I just realized I opened up the wrong way, and I have to restart my computer to make it work. Great! Okay, so in between class and Stinger, I will restart my computer so I can show you. Okay, I'm sorry guys. That's what I get for... Yeah, nice try. Okay, so again, what we're doing is essentially the same thing as before. We're going to establish, instead of establishing our radius, now we're establishing what our side length is. And then it's just area of our cross section. And as you can see, these area formulas is usually something side squared, something side squared. So if you just remember those coefficients, that gives you a shortcut. Now notice that these are not all of our shapes that we can do. They could ask us about rectangles. They could ask us about trapezoids. So just a reminder that your area formula for a rectangle is base times height. And so they have to give you some more information. Is your height a constant height? Does your height change? They have to give you more information for that. And our area of a trapezoid. Ooh, what is our area of a trapezoid? Good. 1/2 height, base 1 plus base 2. I'm going to say h over 2 base 1 plus base 2. And again, they have to tell you some information about this. Is it which base is on your region, whatnot. So they'd have to give you some more information for that. I would say that the most common ones are going to be the shortcut formula ones. And you do want to make sure you know the difference between your isosceles right triangle with the leg on the region and your isosceles right triangle with your hypotenuse on the region. They will specify which one they're talking about. Okay, so number 1, find the volume of the solid whose base is bounded by these lines. Let's go ahead and sketch our graph. Let's see, I'm going to rewrite this just so it's easier for me to visualize what's happening. At -1/2 x plus 1 and 1/2 x minus 1. Okay, so I've got y intercept at 1, y intercept at -1. Okay, that's that. Okay. So we've got 1/2 x plus 1, -1/2 x plus 1. So that was my f of x function here. And then I have x squared for this function. All right, so this is the base of our region. Okay, so this is the base. Again, we have that flat surface. So this is going to be similar to this example we have here, where our base is kind of that triangular base. All right, so our cross sections that are coming out of here are equilateral triangles. All Alright, so again, what we have are a bunch of different little equilateral triangles right now. The equilateral triangles we know is that whatever our side is here, it's the same for all of them. So I'm just going to exaggerate it, but I have a bunch of little triangles coming out. Okay. And so we can see that it's going to kind of start out large and then slowly get smaller because again, our side is biggest at the beginning on the left side, and then as it goes to the right, our side gets smaller. So what we're doing now is instead of establishing our radius, we're establishing our side. And our side lies on the region. And so it's really just, again, doing that top minus bottom, top minus bottom, top minus bottom. So my side goes from the edges, the top edge to the bottom edge of a region. So top minus bottom, my top function was my f of x. My bottom function was my g of x. Let's see, f of x was 1 minus x over 2. G of x was negative 1 plus x over 2. So again, we're just doing top minus bottom. Let's go and simplify this a little bit. We get 2 minus x. Is that right? Okay, so I know that my side is going to be linked to minus x. So again, all we're doing is finding the volume. And our volume formula is that integrating our area of the cross-section for equilateral triangles, our area of the cross-section was root 3 over 4. Side squared. So I have 3 over 4 side squared. And we're going perpendicular, it says perpendicular to the x-axis, so we're going with respect to x. Okay, so now all I do is throw in my area formula with this particular side in it. Integrate. Remember my root 3 over 4 out. What are my bounds? I'm going with respect to x, so I'm starting at 0. Where do they intersect? 2. I just simply counted my slope to figure that out. Okay, and then my side squared is 2 minus x quantity squared. And we just integrate like one. So we're going through the same process. We're integrating the area of our cross-section. Just now we're not rotating, so we don't have circles as our cross-sections. We instead have equilateral triangles as our cross-sections, and our area formula for that was root 3 over 4. Okay, so let's go ahead and do this one by hand. The other one's do by calculator. All right, let's see. We get 4 minus 4x plus x squared. Integrate that. Root 3 over 4. Right-hand side derivative. 4x minus 4x squared over 2, so 2x squared plus x cubed over 3. Evaluated from 0 to 2. So I have root 3 over 4. Over 2, put it in, I get 8 minus, is that 8? Yeah. Plus 8 over 3 minus 0, 0, 0. So our answer is, those cancel. So we get 8 root 3 over 12. Or we can simplify that. Okay, I'm getting ahead of myself. I'm sorry. Root 3 over 4 times, let's simplify out to just 8 over 3. Let's reduce. So I get 2 root 3 over 3. Technically, our units would be units cubed. I don't know that I've ever seen them ask for units on volumes with rotation and cross sections. So who knows? Maybe this year they do. But it's a volume, so you're talking about units cubed. Again, on AP 3 spots, please stop here. But our final answer is 2 root 3. Is that right? Yes. Questions with that? Okay. So again, doing a lot of integrating. I would recommend you do a few by hand, but hopefully we are pretty solid in our understanding of integrating. So you may use your calculator to speed the process up. Okay. So here, different base. So we've got our circle. Alright, so one solid space is this region. So this is our base. This is our flat surface with which we'll be having shapes coming out of this way. Okay. And it says cross section is taken perpendicular to the y-axis. Alright, so perpendicular to the y-axis. So when I draw my squares, I have to go perpendicular to the y-axis. So we're getting squared. Okay, so interestingly, I don't think it actually changes your volume, even if it's perpendicular to the x-axis, because it is a circle. Normally, when we have a perpendicular to the y-axis, that does change your volume. Okay, so a bunch of squares coming out at you, and so our side is again based upon our region here. Now, because we are perpendicular to the y-axis, that means we have to go with respect to y, so dy. So I need to change everything to be in terms of y, which this already wasn't even solved for either thing. So now we can go and solve for x. We get x equals plus or minus the square root of 9 minus y. Subtract y squared over x squared. So what I have then is this side is my positive root, so root 9 minus y squared. And this side is my negative squared, so negative root 9 minus y squared. Okay, so when I go to establish my side, again, same thing as before, top minus bottom, right minus left. Here we're going with respect to y, so I want to do right minus left. So right function, which is square root of 9 minus y squared, minus, so right minus left, my left function was negative root 9 minus y squared. Plus a positive, so what I get is 2 root 9 minus y squared. Which makes sense because it's just double. So that's my side. Again, my volume is the same formula, and that we are integrating the area of our cross section. We're dealing with squares, so our area of the cross section is just sine squared. So when I go to do my volume, I'm integrating the area of my cross section, which is just sine squared. I'm going with respect to y. So let's go and fill in what we have. What are my bounds for this? Yeah, and that actually didn't change even though we're going with respect to y. Alright, then my sine squared, so I have 2 root 9 minus y squared. I want to do squared of y. Okay, and then from here we can go simplify. Guys, again, the biggest mistake that people make with this is forgetting their squares. So number your square. So we can go ahead and integrate this. We have negative 3 to 3. We have 4 times 9 minus y squared. Oh, this one's not too bad. I want you guys to go and do this one. This one does come out to relatively nice for sure. Not relatively nice. Guys, I'm going to pass around another cross section. This is the same base as our other one where it's a circle, but our cross sections are little triangles now, so you can kind of equal out our triangles. So you can see how the shape differs, our solid differs based upon the cross section. So I'll pass that around as well. You guys could have obviously distributed your 4, cut the 4 out, either way. But distributing, we get 36 minus 4 y squared is equal to y. Then when you integrate, you should have gotten simplified down to just 144. Yes. So this is where this is going to be the first shape that I passed around. Sorry. First shape that I passed around where it's a circle with squares coming out. So you can kind of see with this shape here, I've got my solid up here. Because my sorry. Because my squares change in width as we go along. My squares, you can see, are really small and they get bigger. You can see it's like a cylinder got shaved off. Okay. So guys, I'm gonna pass this one around as well. This is just a bunch of the little cross sections. How cool is this, by the way? A bunch of the little cross section squares put together. You can see the little square is smallest on the edge and it gets bigger as we go. So it's kind of like a cylinder got shaved off. Pass this one back. Okay. So we've had equilateral triangles, we've had squares. Let's try something else. Ooh, let's do number 4 next. Rectangles. Rectangles are not difficult, and I feel like when people see them, they're like, wait, what's the area of a rectangle? And they freak out. So let's do it so you don't feel like it's too hard. Ignore the fact that there's random things in red. Microsoft Word went crazy on me, and I thought I could. Okay. So it says, find the volume of the solid whose base is bounded by y equals sine x from 0 to pi. That's important. Parallel cross sections perpendicular to the x-axis are rectangles with a height of 4. So let's start off with our region. We have sine of x going from 0 to pi. So our sine of x graph is like this. We want to go from 0 to pi. We have this region here. And so our base, this is what our base is. And we have rectangles coming out at us. And the rectangles all have the same height of 4. That's super nice for us. So our rectangles have a height of 4. So they are perpendicular to the x-axis. So I'm going to draw a little rectangle here. Obviously this rectangle will be even bigger. So we have a bunch of little rectangles coming out. They all are a height of 4. Okay, so again, let's go ahead and establish what our side here is. I'm just going to focus on this rectangle. Okay, so my side is based upon my region. And what did we say the height of a rectangle is? It's 4. All right, so let's go ahead and establish our side here. My side is again top minus bottom. My top would be sine x. My bottom is just 0, so it's really just sine x. Okay, when I go ahead to integrate, again my volume equals integral of the area of our cross section. It's a rectangle, so I'm going to say base times height, going with respect to x. Well, my base is just my side here. And my side, we set to sine x. And the height is the same. The height is 4 for all of our rectangles. And let's see, we've got going from 0 to pi. So rectangles are not difficult. Again, it's just base times height. Your base will be lying upon your region. Your height, they have to tell you something about it. A lot of times they do just a standard regular height of a solid number. Sometimes they'll say something like your height is twice the base, or your height is half the base, something like that. Okay, so what we really have then is 4 is the integral of sine x dx. And then we just integrate this. So I think this cross-section that was done over here, yeah, so this cross-section here was rectangles with just a standard height of 3. So you can see that the height of the rectangles coming out at you is the same, right? That did not change. Whereas our triangles, the point at which they came out at you, that changed because their triangles width changed. But for our rectangles, they gave us a standard height of 3. So the height of 3, the point at which it came out to, was the same with the time. Alright. What's our antiderivative sign? Good, negative cosine. Well, this one's not bad at all. A negative 4 cosine of pi minus negative 4 cosine of 0. Let's see. Cosine of pi. What's cosine of pi? Negative 1. Negative 1. And then what's cosine of 0? So we've got positive 4 plus 4, so 8. That's a nice little volume there. Okay. Questions with that? Okay. So again, you just simply set up your region and then draw your shape-based quadrant. So let's go ahead and set up 3 and 5. And we'll use your calculators for those ones. So for number 3, we've got the line x plus 4y. X equals 0, y equals 0. And they're perpendicular to the x-axis. So let's figure out what this line is. So yeah, 4y equals negative x plus 4. So y equals negative 1/4 x plus 1. Okay. Alright, so let's go and just do a rough sketch of this. We've got 1. Alright, so it starts off at 1 for y-intercept. It's down 1. Alright, so it's bounded by this line, x equals 0 and y equals 0. So outer region. This here. Alright, and our cross sections are semicircles. Yes, sir.
On the last one,
Yeah.
are all of the rectangle heights, are they all height of 4?
They're all height of 4. Yep. Yeah, so like this guy, how the rectangles all come out at the same height. These were also a standard height of, like this one was a standard height of 3. Whereas like here,
That one's different.
the triangles are not the same height because these ones were isosceles right triangles. So the height of them depended upon the width of them. So you can see that they come out at different heights.
Okay, thank you.
Alright, so we've got our region here, and it says we've got semicircles.
No, I just want to know where it come from.
This one is from Foster Manufacturing Company in Plano, Texas. I like these ones where it's the solid. That had taken a lot of work to do because what they did is they sliced up all of those triangles, laid them real nice. They did to get the different.
No, they didn't. It's
I
just
thought it was
piece
just
of
like
wood.
Yeah, you have to make it. You can't. Wood doesn't look like that.
Thank you. It's like a bunch of little slivers of wood that they glued together and sanded real nice.
Oh, it is?
Yes.
It's a lot of work to make this sucker here.
That's not what it is.
Sure, this one's a little different. This one's our triangles.
I thought it was just the grains.
No.
We didn't see this one yet. No, not this one.
We didn't put under.
Okay, so we have semicircles coming out here, and our semicircles lie on the base. So again, my side of my semicircle is based upon our region here. And so when I establish my side, it's always top minus bottom. My top function is negative 1/4 x plus 1 minus bottom, which is just 0. So we really just have is negative 1/4 x plus 1. And since we're doing semicircles, our area formula for the semicircle shortcut was pi over 8 side squared. So when I go to do my volume, and volume equals the integral of my cross section, area of the cross section. And we're going with respect to x because it's perpendicular to the x-axis. So I'm going to bring out that pi over 8. And we're going from 0 to 4. take a 0 and put it in. Y equals 0. Y equals 0, put it in. X equals 1. Alright, my side squared. Negative 1, 4, x plus 4. Yes. Now we could do this by hand. Save on time though. We get an answer of pi over 6. Questions with that one? Alright, let's go take a look at our picture down here. Alright, again, ignore the fact that there's some of it in red. Alright, so our base, we have a parabola and a line. Cross sections are perpendicular to the x-axis. We're going with respect to x. Cross sections are isosceles right triangles with our legs on the base. So it means our legs are on the base. Okay, let's see, we've got a parabola there. Y-intercept of -3. It does not factor nicely, that's alright. That's a bad representation because it doesn't actually, it's not necessarily our minimum, but that's okay, we're just trying to get an idea of it. Can we find some points now? We're zooming. Okay, and then y equal to x. Okay, so we're looking at this region here. We've got to figure out where those intersect. Alright, and it says that we have cross sections perpendicular to the x-axis, and these are just isosceles right triangles with the base. So I'm just going to draw one of them. Alright, so here's my side, and my shortcut when my side is on the base, remember it's just half of the square, so it's 1/2 side squared when my side is. Alright, so again, to figure out my side here, we do top minus bottom. So my top function was just x minus my bottom function, which was this parabola. And it's the same function on top the whole time and same function on the bottom the whole time. So we don't have to split it up. My bottom function was x squared minus x minus 3. So we get negative x squared plus 2x minus 3 is my side. Okay. Plus 3. Thank you. Alright, so again, when we go to integrate, we're just doing our volume is the integral over area under cross section, which we said is 1/2 side squared. And bring my 1/2 out in front. My side squared, negative x squared plus 2x plus 3 squared. We've got to figure out our intersections there. How do I find my intersections again? Yeah, so it's an equal sign. X squared minus x minus 3 equals x. Subtract x over, so x squared minus 2x minus 3 equals 0. So x minus 3, x plus 1, x equals 3, and negative 1. So negative 1. Again, we could integrate that by hand, but to save on time, we get an answer of 256 over 15. Is that what you got? That real quick mental math, right? So again, our process is the same. We're integrating our area of the cross section, just our cross sections are no longer just circles. If it's rotated, it's still a circle. But if it's not rotated, they have to say what your cross section is. Instead of finding radius, we're finding our side length, and our side length is just top minus bottom or right minus left. Okay. Any questions with that? Okay, let's squeeze in this last one. I just want to make sure we're clear what to do for this. So here it says we have a horn for public address system and PA system. And it says it will have the shape of the solid form when the region is rotated about the x-axis. We are rotating here. So we are back to doing the big R squared minus little r squared. Okay, so I just want to make sure that we don't get so caught up in our cross sections we forget about this. When it says rotated about the x-axis, we have big R squared minus my little r squared. right? We're rotating. We've got our shape looks like this. Something like this.
Are those supposed to not be straight? The R's and H's?
So H.
Or
Oh,
big R, little R.
Big R, little r. They should be perpendicular to the x-axis. Oh, golly. Yeah, that's not perpendicular.
I was just
It
wondering.
looks great from my angle. Okay, so again, we have solid, we have big R squared, minus little r squared. We'll finish that and then I'll let you guys go. So again, pi, big R squared is top minus bottom. My top function is our, let's see what we have here. What is our top function? Yes, thank you. X plus 1 is my top function. So my big R is x plus 1 minus my little r, or sorry, top minus bottom. So top function is x plus 1, bottom function is just 0. So my big R is x plus 1. And then my little r, top minus bottom, top function was e 0.4x minus, again, 0. So we have e, so 0.4x squared dx. This one was definitely calculated. But again, we have rotation, our cross sections are circles, we have pi r squared. And the answer for this one was 26.64. So if it says it's rotated, then if you're going back to our cross sections, they're going to be circles. But if it's not rotated, it's going to be cross sections. Okay, go ahead and take a break, come back. If you did not make sure you know how to complete the square, I recommend you quickly look at a video or look something up online in these next 7 minutes. And I'll go ahead and restart my computer and pull up the Geometry Sketchpad file that shows you the cross sections. Yeah, guys, I think looking at our assignment sheet, we have a quiz next class, don't we?
You said you did, remember?
No, I didn't. Nice try. Yeah, we do have a quiz next class.
No, you did.
We all over our volumes and our average value with the what's the other thing? Everything's with curves. What's that?
It's not that we're on
Yes. Yeah. All right, and I'll pass out your homework to you as well.
There's so much editing.
Again, guys, for your homework, you are welcome to use your calculator, set it up, do a few by hand, but then you are welcome to use your calculator to evaluate it so you don't have to spend all day long doing integrals and polynomials and whatnot. So guys, here's your homework coming after. Did we assign something for you too?